Hello, and welcome to my talk. I'm Ido Dagan from Bar-Ilan University. First, I'd like to thank Ken Church and the organizers of the workshop for inviting me to speak at this event, and I'm looking forward for the live event on Thursday. Giving some context to my talk or general motivation for the content I've chosen for my talk, like everyone, we are all happy with the huge progress that NLP experienced in the last in recent years. And of course, it became practical and beneficial for many applied settings. However, we should remember that in fact, there are many more settings for which leveraging NLP would be great, but our technology isn't good enough for these settings yet. And it's not that we necessarily expect that next year we'll get there. Definitely, there are certain situations in which current technology seems to be facing certain glass ceilings. So in this talk, since benchmarking is kind of the vehicle to drive empirical research, I chose to speak about three directions where I think we might be taking NLP benchmarking in ways that will help to drive our field further. And these three aspects I'm going to talk about the first one is methodological, refers to benchmarking methodologically. And it focuses on the need that when designing a benchmark, it's important to simulate the realistic data and usage scenarios for which models are expected to be used. The second aspect in benchmarking is about benchmarking NLP applications. And here my main message is going to be to try to drive NLP benchmarking towards many more interactive settings of interactive NLP applications. And thirdly, at the dimension of NLP infrastructure, I would suggest to revisit the benchmarking of generic semantic or open knowledge representations that are used as generic infrastructure in certain directions that I find suitable, particularly for this era. And in a certain sense, for all three parts, I think that where we are today might be related also to certain kind of comfort zones aspects that explains the use of this term in the title of this talk, while the directions I'm proposing might help us get maybe a bit out of these comfort zones, but in promising ways. So let's start. The first part then is methodological, about simulating realistic data scenarios. So what's realistic versus comfort zone? Just kind of as a teaser, of course, comfort zone is simple, right? We are at our comfort zone in benchmarking if it's easy to collect the data. So the benchmark creators are happy. It's easy to model the data. So then model developers are happy and are encouraged to publish their papers. Everyone is happy. But what is realistic? At the end of the day, we develop NLP models which are aimed as an applied field, aimed to be useful in some practical settings over some real-life data and usage scenarios. And therefore, it's kind of obvious, but people might be forgetting that once in a while. We should design our benchmark in a way that would, as best as we can, simulate these downstream use cases. And this simulation should be both with respect to the data composition, as well as to the evaluation protocols that we are applying. In this part, I'll give three examples, three kind of use cases in works I've been involved in that aim to make benchmarks more realistic. The first two, few-shot relation classification and cross-document coreference, come from two recent works published in 2021, while the third one is about textual entailment, RTE or NLI as it was called later, And I was assuming that I cannot give a talk about benchmarking without referring to textual entailment, so I'll touch more briefly, give some perspectives, some kind of retrospective perspectives about this aspect. And with respect to benchmarking aspects, the first talk, the first part, the first use case and the last one will concern more with data composition, while the second one will concern with evaluation protocol. So let's look at the first. Revisiting few-shot relation classification. This is based on a paper that was just recently accepted to tackle. Actually, the final version was already approved, and it's already in archive, not yet online on tackle. The primary author here is Ofer Sebel, a master's student of mine. So what is supervised relation classification? I'm assuming everyone is familiar with the task, but basically a relation classification instance is given two entity mentions, often in the same sentence, but not necessarily. We are asked to classify the relation between them, where the target relation is taken from a predefined set of possible target relations. So when people build typical relation classification data sets in the standard supervised setting, they sample instances from a corpus. Some instances correspond to the target relations, but in order to simulate a realistic scenario, some candidate instances actually correspond to a special category called nota, none of the above, meaning that in this case, there is either no relationship between the two entities, or might be some relation, but it is not one of the target relations. And TACRED is a nice example of such data set. Like any data set, it has some pros and cons, but overall it's kind of a sensible data set developed at Stanford, including some statistics. And then, as you can see, it also has kind of a typical long tail distribution of relation frequencies, noting that this is 1,000 instances, 2,000, etc. So many relations actually have like hundreds or at least dozens of training of instances. The supervised setting is nice, and we have good models for that. But in a sense, a much more realistic setting for the relation classification task is the few-shot setting. Because when a user in the wild have some relations of interest, it's not realistic to expect often that that user would be able to annotate hundreds of examples per relation, per target relation type. The few-shot setting assumes that for new user-specific relations, only few training examples would be provided. And indeed, at 2018, the FuRel dataset came out, the first few-shot relation classification dataset. And the basic setup there is that you have many background relations. So we do assume the availability of some generic supervised training data for relation classification as in general, but not for the specific target relations with which each user will be interested. While there are few new target relations on which we are going to test the system, and for those only very few training examples will be provided. And then there's some notion of episodes on which evaluation is based. And this is a large data set. As you can see, 100 classes, 80 training, 24 tests with 700 instances each. Of course, in the test cases, we don't, in each particular test instance, we only use a sample of a few training examples according to the few-shot setting. And then there was FuRel 2.0, an extension of the FuRel dataset, which also incorporated the nota category, none of the above, which was missing in the first one, to make it address a more typical scenario. And indeed, these two datasets encourage research on this very important few-shot setting. However, working on this dataset, we noticed that it lacks some important properties that one would expect from a realistic dataset. First, one would expect that the dataset would cover all entity types, including pronouns, common nouns, but FuRel covers only named entities. Second, in a realistic data set, some relation instances may not have any relation at all, not just not and none of the above, but maybe some don't. For some instances, there is no relation whatsoever between the two entities, as you see in this example. I mean, London and Tel Aviv are both entities mentioned in the sentence, but there is no sensible relationship between them. These are missing from a Furel. Next, the distribution of relation types. As you could see in a natural data set like TACRED, there is a typical long tail distribution. In Furel, by design, all relation types have the same number of instances, which kind of makes a somewhat unnatural setup. And finally, the nota rate, this kind of none of the above case, where you get a training instance and actually you have to say it's not one of my target relations, is rather low and was arbitrarily set to 15 or 50% in two settings in Furel, while realistically, when we examined the TACRED dataset, for instance, we found that it's more like 95%. And of course, nota instances make the task harder. So given all these non-realistic properties, indeed, the Furel dataset ends up being very easy, and state-of-the-art systems reported accuracies in the range of 80–85%, even in the hardest one-shot setting, only a single training example. So our goal is, while working on future relation classification, in addition to developing models, was to create or develop a dataset with a much more realistic data composition. To that end, we revisited the TACRED dataset, which, as we said, as we could notice earlier, does satisfy all these desired properties that I mentioned. Yet TACRED is a supervised dataset. So what we wanted to do is to somehow come up with a generic procedure for transforming a relation classification, a supervised relation classification dataset, to a few-shot relation classification dataset. And the main difference between the supervised and the few-shot setting is that in the supervised setting, you have, as usual, you have a train dev test split, but in the supervised setting, you have the same categories across all splits. While in the few-shot, as we've seen, the training set should include only background relations, while in the test set, you are testing about new categories. So our goal was to preserve kind of the original distribution of relations in TACRED, the natural one, but apply a general transformation scheme that would transform it to the few-shot setting. And this is the scheme we came up with. I'm not going through the detail, but the general idea is that in addition to the train dev test split of the instances available in a typical data set, like a supervised data set, we also added a train dev test split of the categories of the relation types, which means that if, for instance, a certain, in this case, like C relations are test relations, all other relations will be kind of marked out from the test data, meaning that all instances of other relation types will become nota relations in the test set, and similarly in the training and dev. So you can look at the paper for details, but basically it's a generic, a bit subtle, but actually somewhat simple procedure for satisfying the few-shot setting, still with episodes as in Furel. And this results with an appropriate data set. And indeed, with respect to relation distribution, we could see that few-shot TACRED, our new release data set in this paper, has a natural relation distribution similar to TACRED, but the nota rate is high. Notice this is a log scale, while Furel, as we've seen before, has just an even distribution and arbitrary ratio of the nota relation. This property indeed makes TACRED, few-shot TACRED more realistic, but also much harder and much more challenging. In fact, in that paper, we developed a new SOTA model that achieves SOTA results on Furel 2.0, 73 F1, this is F1 measure, but on the few-shot TACRED, it achieves only 21 F1 points, meaning that actually current technology, state-of-the-art technology, the type of models that people are using, and we have kind of introduced some innovations, again, you can look at the paper, is really not sufficient for coping with realistic few-shot setting, suggesting that substantial future research is needed. So this was an example how people might come up with a new data set, seemingly with a nice composition for a very appealing setup, the few-shot setup, but the data composition unrealistically makes it too easy. The second work I'd like to mention briefly is about how to make an evaluation protocol more realistic. This one regards coreference evaluation, particularly in the cross-document setting, but actually the principles are, most of them are relevant also for within document coreference resolution. The lead author here is Aryeh Katan, and this is a paper coming up this week at StarSem 2021. So what Aryeh noticed is that reported results in recent years over the standard dataset for cross-document coreference, namely the ECB class, don't seem to reflect realistic performance for three reasons. One is that there's been a habit in recent years to evaluate only on gold mentions, while we know that models should be challenged with predicted mentions. There is some aspect on which I'll elaborate in the next few slides that evaluation protocols on these data sets did consider singleton clusters, which, as we see, makes some undesired biases and inflates performance. And there's also another aspect, which I'll skip in this presentation, that these protocols found a way to kind of sidestep a lexical ambiguity challenge that this ECB plus dataset tried to impose in its data composition. So let's focus on the second aspect, the singleton effect in coreference resolution. And I'll illustrate this effect in a single document coreference task, but it's really the same in the single document or cross-document setting. So let's examine first to understand what is the desired behavior of a coreference evaluation protocol that would simulate realistic downstream use. Let's look at a typical downstream use case example for coreference resolution. So we have here a text, and we have a question: who does the clan get into fight with? And it's reasonable that in order to answer this question, the system would have to recognize that the them in the clan fights them co-refers with 3 van thieves, which would allow us to obtain the correct answer that the clan that was fighting 3 van thieves. Oops. Sorry for a second, it went out of present mode. I'll just get it back. Okay. So we see that in a typical use case, downstream applications would use coreference resolution in order to identify links within a coreference cluster, and this way bridge information from one mention to the other. And this is, of course, relevant only when the output consists of non-singleton clusters. There's only one element in a cluster, one mention. There's nothing, no information to bridge here. Let's look now at the effect of this observation on the consideration of singletons in evaluation, in cross-document coreference evaluation. So imagine that this is the gold, and it's not just imagining, I mean, for the example text we've just seen, this is the gold coreference annotation. We have here 5 single clusters and 2 non-singleton clusters. And now imagine one system that performs pretty well on the singleton clusters, but not so well on the non-singleton clusters, and in fact merges these two clusters, versus another system that maybe might perform somewhat poorly on the singletons, but does pretty well, not perfect, but pretty well on the non-singleton clusters. From the observation we just noticed, we would say that S2, the second system, is preferred because it would help downstream applications to better recognize coreference links. But if we look at the way people applied the typical coreference evaluation measures, these are the kind of typical coreference evaluation measures over the ECB plus corpus, where they did consider singleton clusters, we find out that actually by the common practice, the first system would score 76, while the second would score only 59, seemingly favoring the downstream, the first system, but actually being counterproductive for system choice for the purpose of downstream use. On the other hand, if we follow the protocol that is common actually for the within document coreference dataset, the prominent one, the Connell 2012, which doesn't include singletons. I'm not sure if it was by design or just by saving some annotation effort, but anyhow, it doesn't include singletons, and therefore, when people evaluate there, they don't consider singleton clusters, neither predicted nor goal. When we would remove the singletons from the evaluation, indeed, we see a score that clearly favors the second system. Notice that if the system would wrongly take a singleton and put it wrongly in a non-singleton cluster, it would still be penalized on that. So when singleton harms in detecting coreferences, the score would be penalized. Still, some people would argue that, okay, how can you throw singletons all together? They might be relevant for mention prediction, in case we got such a reviewer comment on that point. And that's true, but what we propose that we should actually decouple the mention detection aspect from the coreference resolution aspect. Mention detection can be evaluated separately, as typically for mention detection as a span detection task, while coreference should be evaluated by the typical coreference resolution measures that are focused at measuring how well a system identifies the coreference links that exist in the text. And this suggests that we might evaluate indeed coreference links by the Connell, by the typical coreference measures favoring system 2, while we might apply standard span F1 to mention detection and figure out that actually for mention detection, system 1 is preferred. And there was also another aspect discussed in this paper of suggesting to avoid a certain clustering aspect that was common in recent practice, evaluation practice, that actually kind of neutralized a lexical ambiguity challenge that was posed by design in the ECB plus dataset. But what's important, similarly as before, is that if we take the model we've shown, which actually surpassed prior state of the art, it's not exactly state of the art today. State of the art today is a few points higher by now, but this model definitely demonstrates the issue. We see that this model obtained state-of-the-art result. At the time was 81 Connell F1 points. But then if we removed singletons, performance decreased by about 10 points. If we removed this kind of clustering of topics aspect that people were using, the model lost another 9 points. And then if we applied it to predicted mentions, we lost another 13 points. Altogether, yielding a 32-point decrease and a fairly low performance for current models, again indicating that actually current models do not cope well with realistic scenarios as expressed by or as captured by the evaluation protocol. So this would be the takeout. Again, a similar takeout to the first work that I overviewed, but in the first work, it was about data composition, and here it was about careful evaluation protocol. Finally, for this part of realistic evaluation methodologies, I would like to revisit the textual entailment, or as it was later called NLI, benchmarking. So textual entailment, as we actually introduced it in my group, back in 2005 and later was termed natural language inference, somewhat more vague term in some data sets, is a generic infrastructure NLP task. And the reason why it caught up as such a prominent task is because we have shown that textual entailment captures semantic inferences in many other downstream applications in natural language or tasks in NLP. And we were showing that in these tasks, various types of inferences can be reduced, can be kind of translated to the entailment recognition. So if you would get a powerful entailment recognition model, you could plug that model later in many other tasks and use it to improve certain inferences within these tasks. So being such a generic infrastructure task, what does it mean to have a realistic textual entailment benchmark? So to answer that, let's look a bit deeper into this aspect that application-specific inferences can be reduced to the entailment task. So let's look at a question answering example. Suppose we have a question, who acquired Overture? One thing we can do before answering the question is actually translate or transform this question to what we maybe call as an expected answer template. So it's a template of an affirmative form, which indicates how the answer sentence should look like after plugging in the correct answer instead of the variable. So basically, we are looking for some sentence X acquired Overture, where the correct answer for who acquired Overture would substitute X here. So that's just another way to look at the question. Now, suppose we manage to fetch this text, Yahoo's buyout of Overture, blah, 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 mentioned in a longer text. From this text, we can infer what the correct answer is, right? We can infer that, in fact, Yahoo is the company who acquired Overture. But what's the reason that we can, for which we can infer that Yahoo is indeed the answer to the question? We can see that if we plug now Yahoo into the answer template, we get a statement, Yahoo acquired Overture. And the reason that the Yahoo is the right answer based on this text is because this text entails this instantiated answer template, okay? So if the text entails the instantiated answer template, it means that the answer is correct. If the given candidate passage would not entail the instantiated text, that would correspond, equivalent one-to-one correspondence to a case where the answer is incorrect, right? If we would put here some other company, we wouldn't get an entailment here. So this really means the reduction. This illustrates the reduction from some kind of application-specific inference, like validating a correct answer in question answering, to the entailment task. But this kind of reduction is not unique to question answering. I mean, it can actually happen also in other applications. In relation extraction, we could have a relation extraction instance with template X acquire Y. And if we get this text, we would like a relation extraction system to extract Yahoo as the acquirer and Overture as the acquired company. If we would plug these two extracted entities in the template of the form X acquire Y, which captures the target relations, we would indeed get an entailment that Yahoo's buyout of Overture entails Yahoo acquired Overture. And again, there would be a one-to-one correspondence between a correct extraction and an entailment case versus incorrect extraction and incorrect entailment case. Notice, as you look at these two examples, that actually each of these examples gives rise to an instance of the entailment task, right? We could give an entailment task these two sentences and ask the entailment system to recognize whether entailment holds or not. Or we could plug here an incorrect answer and still give this supporting passage for Yahoo and expect an entailment model to recognize that there is no entailment in this case. So this reduction also gives us a natural process to derive entailment questions from inference instances in other applications. And this holds for more applications like in summarization, MT evaluation, educational applications, and many more. And indeed, in the last 15 years, we've seen people plugging in entailment models in many other applications. So now let's get back to our question. What is a realistic setting for NLP benchmarks? When we designed the early textual entailment data sets, indeed, we followed this kind of reduction from various applications. And we created entailment instances exactly by taking instances from data sets for other tasks. Specifically, mostly we use QA, RE, and summarization data sets, from which we derived entailment instances that simulated inferences needed in the original application. This indeed yielded, in a sense, instances that represent some realistic inference cases in various applications. And also another thing to notice that in these cases, usually both the premise and the hypothesis were based on original text derived from the original application data. In 2015, there has been a shift with the SNLI and later the MNLI dataset, where the methodology was different. The authors of these datasets collected natural text snippets to be the premises, but then they presented them to Turkers, crowd workers, and asked them to synthetically generate out of the mind one entailing hypothesis, one contradicting hypothesis, and one neutral hypothesis. This is a completely different generation process, and it's not very clear in what sense it is a realistic one. It kind of captures the process by which people invent different types of hypotheses, but it's not clear how it directly relates to the downstream use cases of entailment. As I mentioned, I mean, the whole point about realistic benchmarking is about creating benchmarks that simulate the downstream use of the models you develop using your benchmark. So to wrap up this part, my proposal is to derive RTE and NLI datasets to revisit the original approach and to try and derive large RTE or NLI datasets from large-scale datasets in various applications, as well as system outputs, because often you have to plug in also the system output in order to create positive and negative examples. And this might be done with recent reading comprehension datasets, fact verification datasets that evaluate for summarization factuality, relation extraction, KBP, etc. Many datasets in which the underlying inference, semantic inference, is in fact entailment. And from these datasets, I suggest there is a potential to generate large-scale datasets for textual entailment that would have a much more natural composition. So the takeouts from this part is that when you design a benchmark for a task, consider carefully the typical downstream use of the models that would be developed based on your benchmark, and then design both your data composition and your evaluation protocol to simulate these usage scenarios. And you have to watch carefully for subtleties, as you've seen both in the relation classification dataset and the coreference resolution datasets. The issues were subtle: the relation distribution, the proportion of the nota category, whether to consider singletons or not. These were all aspects that were kind of were not noticed in prior research until we noticed it in our work, and much of the credit deserves to my students that noticed these aspects. And then such benchmarks, as we've seen, may expose the deficiencies of current models. Performance might drop significantly, but on the other hand, it might push research forward to confront the realistic challenges. So this was about the methodological aspects I'm trying to promote, and key methodological aspect I'm trying to promote in the general methodology of designing benchmarks. Now I'd like to move on to the next part, where I'd like to propose one certain direction in which we can extend the scope of benchmarking NLP applications, and particularly towards the interactive settings. So as we know, most NLP benchmarks regard offline tasks. Again, kind of a comfort zone, right? It's much easier to handle a static corpus of which you just, static dataset of which you just run your system, and that's all. Yet, there seems to be a huge potential for NLP in interactive systems. And these interactive settings are, in fact, rarely investigated today apart from dialogue system. So dialogue field did manage to evolve as an interactive setting, but there's a lot of potential for interaction in NLP beyond dialogue, and that's what I'd like to advocate. And specifically here in this part, I'll illustrate this general kind of proposal for the case of summarization. And specifically, I'm going to illustrate the direction we're developing for interactive summarization, and of course, with an appropriate benchmarking paradigm. And that would call for analogous developments also for potentially for other interactive settings for other NLP tasks. So this part is based on work by whose lead author is Ori Shapira. It just appeared recently at NACL with colleagues from also from UNC and a college in Israel. So what's the motivation behind interactive summarization? We all love summarization because we can take many texts and instead of reading them, we just get a short summary. But then what happens if the topic embedded in this text is indeed of interest and we figure out that we want to know some more? In that case, with static summarization, our only choice is to go back, to the mess of original text and somehow figure out our way through them. What might make much more sense here if we could somehow interact with the summarization system, guide it what kind of additional information we look for. The system might hint for us what else might be hiding here that we may be interested in. And by that, conduct kind of interactive session where the user guides the system, poses requests, and the system expands gradually the summary. This would be a nice kind of paradigm for extending the scope of summarization. And indeed, we developed such a demo. For the sake of time in this talk, I'm skipping the demo, just give some screenshots. So there's a few screenshots from our demo system or baseline system, where the system now helps the user to explore a collection of 25 articles on Native American challenges. This is in fact one of the topics in one of the DAC datasets. So what the system first presents as an initial summary, like a typical, fairly short initial summary. And the user may see here, may discover in this summary two main challenges. One is about dependency on federal funding, and another is about gambling. Now the user may be interested in knowing more, so the user might highlight gambling, which would then actually put gambling into the query box, and now ask to get some more information about gambling, and the system would automatically expand the summary with more specific information about gambling. Now the system can ask about other things like maybe federal funding, or may also be interested in aspects that come out of the user's own mind, so just typing in here in a free text query. But the system also suggests queries based on information that it discovered in the text, but did not expose yet in the initial summary. It wasn't salient enough. For instance, the user might discover, there are high school issues. So the user might be interested in educational aspects, educational challenges for Native Americans, and click high school and get more information. So this gives you the gist of how an interactive summarization system might look like. Now, there have been many prior interactive summarization systems. Actually, not many. That was a mistake. There were only a handful, but there were several prior interactive summarization systems. But this line of work hasn't caught up yet. And possibly one of the reasons is because there is no proper evaluation protocols and benchmarks for interactive summarization systems. All these systems were evaluated by different methods. The task itself was never kind of framed in a consistent way that would allow consistent evaluation. So this brings us the question, how can we formalize and evaluate interactive summarization? And that's what we addressed in this paper. And specifically, we propose one way to formalize interactive summarization. Maybe it doesn't cover all potential modalities in interactive summarization, but at least a quite rich scope, which we call expansion-based interactive summarization. So under this perspective of this framing, we view a session as an incrementally growing sequence of snapshots. Each of them can be viewed as a static summary. So we view a session in the following way. The session would start with an initial summary, which would be the first snapshot. Then the user would interact with the system in one way or another, posing a request, and the system would bring some new information based on in response to that request, response one. And then the second snapshot would be the initial summary plus appended with the first response. This would go on then, a second request, a second response, and the third snapshots append that response as well, and so on and so forth. So we see that now the session can be represented as a sequence of static summaries, each of them being a snapshot of the sentences, which, by assuming that the user hasn't forgotten anything or can scroll back to what was presented till now, only expand as the session continues. Okay. Now, based on this formulation, we could design an evaluation framework which is based on these static snapshots, while utilizing standard MDS datasets along with their existing reference summaries, like the reference summary for the Native Americans topic, and using known summarization metrics, both automatic and manual, that we can apply along the session. So let's see how this might look. So for automatic measure, the main measure we were proposing is a recall by length curve, which was already proposed earlier in other contexts. And that is computed against the available reference summaries in a certain dataset, like in a DAC multi-document summarization dataset. So what we see here, we see plots of such curves for two systems. Let's focus first on the, let's say, squared system with the squares, system 2. What we see here at each x-axis point is a snapshot of the system, and the x-axis designates the length of that snapshot in words. As common in summarization, we usually limit summary length or measure summary length in words or tokens. So that's the x-axis, and of course it only grows because the snapshots only expand. On the y-axis, we apply a standard recall measure. It's important to have a recall measure, not an F1 measure. In this example, a Rouge 1, but of course we apply all type of Rouge measures, of common Rouge measures of the recall type. So we can see that at the first snapshot managed to get this level of recall relative to the reference summary, the second snapshot some more, and at the end of the session, we managed to have like 0.47 Rouge recall relative to the original reference summary. So this curve actually measures how fast a system succeeds to bring us more and more salient, relevant information about the topic as captured in the reference summary, and in that sense, measuring the effectiveness of the system. And the effectiveness of the curve as a whole may be measured by area under the curve, as usual, which would capture the overall effectiveness of the system. And then we can also compare two systems, a triangle, a rectangle one, and see which one is better initially, which one might be better later, and so on. So this is about automatic. This is the main proposal about automatic measures. Manual measures can be adapted as well, informativeness, responsiveness, as common in static summarization, as well as usability for the interactive setting, and some of these may be embedded in the interface. The last point to address is how to collect user sessions, because in order to evaluate eventually an interactive system, we must run actual sessions with real users and see how people interact with the system. Now, traditionally, when developing interactive systems, people were conducting user studies as common in the computer-human interface community. But these are often costly and not that scalable, not accessible for any NLP team. On the other hand, one would like to, I mean, most naturally, one would like to apply crowdsourcing. But when we try to apply standard crowdsourcing, we quickly figured out that it's not reliable enough. It was quite depressing, actually, because it kind of questioned whether we can develop or evaluate interactive systems using crowdsourcing. But eventually, what we did is resorting to a somewhat more sophisticated evaluation methodology or crowdsourcing session collection methodology, which follows controlled crowdsourcing. Controlled crowdsourcing is a paradigm that we presented in, it was used also earlier, but we published a paper about it last year in another context I'll review in the last part, which is a more involved process you perform with the Turkers, in which you first find suitable workers through some trap tasks, then you train your workers through some paid training iteration sessions, and you can also promote an objective information goal for all users, all your human subjects, so that you'll be able to compare results across different human subjects. So all these details are in the Knuckle paper. You're welcome to look at them, but overall it works well. And taking it all together, we could see these are examples from actual experiments in that paper where we compared two baseline systems here in the middle. They ended up performing quite similarly to an upper bound, simulated upper bound and similar lower bound. As expected, actual human computer interaction fell in between the lower bounds. This is like an Oracle background, so the user is not as good as an Oracle, but this is like a fully automatic system, and user involvement indeed shows some gains. And these were only initial kind of baseline systems. Of course, we are currently working on better algorithms, developing better interactive summarization algorithms. And we also noticed a trend of consistency between the evaluation measures shown here, the recall by length curve and the area under the curve, this bar, and the manual evaluation measures. So the main takeaways from this part is, for interactive summarization, we argue that it's an important application setting that can really push the usability of summarization much beyond static summarization. For that, we presented an effective evaluation framework which we believe can facilitate research and can allow comparing results across different researchers and across papers as done today for static summarization. And in fact, as I mentioned, we are now working on like better interactive summarization algorithms, and we indeed utilize exactly this methodology. At this point, we are still with the automatic measures. We kind of measure rouge by the protocols I mentioned, and we can use that to guide our development. And eventually, of course, we'll run experiments with actual user sessions and compare to the previous Knuckle paper. Lastly, but then more broadly, of course, I would like to suggest that interaction of this flavor can be useful in many other NLP tasks. You could think of relation extraction as an interactive process, knowledge-based population, question answering when you want to collect multiple answers, sentiment analysis, and so on and so forth. For almost every end task that is important for some end user, it's quite possible that an interactive system would be appealing for such user who would be willing to invest some time in interacting with the system in order to get better results that may be obtained from a fully automatic system. So that's the main message of the second part. Lastly, I'd like to touch quickly on the last part, which concerns with NLP benchmarking NLP infrastructure levels. And here I'd like to touch on benchmarking semantic or open knowledge representations. So the motivation here comes with some historical perspective. When we were in the era of feature-based machine learning, we used to incorporate to extract some semantic structures from text using various semantic analysis tools and feed these structures as input to ML algorithms. Under the end-to-end paradigm, the network is expected or has the potential to identify all these underlying meaning structures on its own. Again, a kind of a comfort zone, right? Because it's much easier to let the system learn it all by itself rather than working hard to figure out how to model various aspects in language. But still, in the E2E paradigm, it's worth noticing, where does the signal come from? How can the where is the potential for the system to learn about, let's say, meaning structures in language from the training it gets. So basically, it has two types of training data, right? One is through pre-training of the language model, which gives some generic objectives and signals, but these are implied, right? We don't have here any explicit supervision. And then the system might pick up additional semantics during fine-tuning, where you do get explicit supervision, but that's usually task-specific. So these are rich signals, as we know. They yield nice results in many settings. But on the other hand, we also observe that in challenging settings, this may not be enough. And these might be examples when you need deeper semantic understanding, portability, interpretability, better control on your system behavior, and so on and so forth. And in various cases, like the two I demonstrated before, when you get really challenging settings, there seems to be certain glass ceilings to current approaches. So as we seek better modeling, deeper modeling of meaning structure in language, we may wish to incorporate further supervision for generic language aspects or meaning aspects that capture human text understanding, and this way we might obtain additional signals by which to train our systems, and then leverage these systems generically in various downstream tasks. And indeed, this is not something, you know, that I'm inventing here. There's quite many line of works that try to incorporate various types of knowledge into deep learning systems in order to improve performance, including semantic knowledge. And there were quite many examples. I just gave a couple examples. A few years ago, people tried to, in these works, to integrate AMR analysis into multi-document summarization. The conclusion here was that maybe AMR, there was some improvement, but AMR was found to be maybe too fine-grained, too detailed for the tasks. So the conclusion was that maybe a somewhat lighter weight representation might be needed. And just this year, these are two examples from TACL. Indeed, people resorted to simpler semantic structures, concretely open knowledge graphs derived from OpenAI extractors, combined with some coreference resolution, and created such graphs that represent the information structure of the text and leveraged these for summarization. In the first work, it was to improve summarization faithfulness, and in the second, it was for improving multi-document summarization. So we see that people do attempt to go this way. And as I mentioned, it's indeed integrating knowledge is a hot theme, including semantic analysis, as I've just illustrated. But we see in these works, including in these works that I've shown, that the research usually focuses on integrating, on how to integrate the knowledge into the deep learning architecture. While the actual semantic knowledge used based on some analysis leverages either existing analyzers like OpenAI extractors or AMR, or uses some fairly ad hoc semantic analysis that were just developed for the sake of this particular application in which the knowledge was incorporated. But if we believe in this direction, it would make sense to try and promote also development of better semantic representations, better semantic analysis models that would give us better output to integrate into the deep learning models. And this has been of less concern recently. This brings up the question, which semantic representation should we benchmark? Which ones should we promote that are most promising for later downstream use? It might be most promising for later downstream use. And here I'm comparing two kind of semantic representation approaches. One is what might be called the classic approach, which relies on pre-specified schemata. We know that most kind of classic semantic representations pre-specify some relation and concept types, semantic row labels, verb senses. AMR relies on certain notions from PropBank. There are other semantic dependency formalisms relying on other formalisms. And this is a typical kind of flavor of a semantic formalism, a classical one. And this kind of flavor or nature has certain consequences. For one thing, inventories of these concepts and types and labels differ. It's not clear which one is the best. they typically require expert annotation to create data sets, and they may have dozens of pages of annotation guidelines. And they're also not well understood beyond the narrow community of the people involved in that particular representation, which also hinders, I mean, all these together hinder the potential use of such formalisms. Indeed, what we've seen, especially in these two knuckle papers that I've seen, that people resorted to some alternatives where the representations are what I call natural language based. The first example is, of course, open information extraction, right? This is an example. Obama was born in Hawaii, 1961, would be transformed to the tuple Obama, comma, born, comma, in Hawaii, comma, in 1961. And these knowledge graphs, open knowledge graphs in these two knuckle works in summarization, indeed created a graph based on these extractions. And it is natural language based because there isn't any other vocabulary here. The elements, apart from some structure, the elements are all just some natural language fragments. What we found is more interesting, still in the direction of natural language-based representation, but going beyond open information extraction that is somewhat limited, is a QA-driven approach, which was initiated by the work on QA-driven semantic row labeling, QASRL. And here the idea is to capture not just the arguments of predicate, but also the role, the relationship between argument and predicate, but rather than capturing it through some formal row label, agent, theme, etc., recipient as defined in some pre-specified inventory of roles, to capture the relationship through a natural language question. So in this case, Obama was born in Hawaii in 1961 would be transformed to three questions. Who was born? Obama. Where was someone born? Hawaii. When was someone born? 1961. And as you can see, decomposing the original sentence to these three QA pairs actually gives you the same information. If you would read the three QA pairs, you would get exactly the same information as you would get from the original sentence. And it's also worth noticing that actually this representation subsumes OpenIE, and the first supervised OpenIE corpus was actually derived from a QASRL corpus. So this was QASRL, originated in the UDAP group of Luk Zettelmoyer, and these are the two main papers. There are more recent papers about it. And in my group, we extend it to cover not just verbs, but also a range of other semantic relationships about nominalizations, other relationships focused on nouns. You see acquisition, height, adjectives, good, all have relationships with other elements in the sentence, as well as work from last year's EMNLP on QA discourse, where we use QAs to capture discourse relations like causality, temporal relations, etc. And the eventual goal is to be able to take a text and transform it to a set of question-answer pairs, each capturing, and so we decompose the information because each question-answer pairs capture a specific proposition or statement expressed in the text, while the overall set of all question-answer pairs aims to cover, as much as possible, the full meaning or the full content of the original text. And we find this as an appealing approach. We go even beyond that. I won't elaborate on this slide, but we even to model multiple texts, not just single text, we develop methods for aligning such information representation, namely QA pairs across different texts. Here as well, because the data annotation is a bit more involved, we follow a controlled crowdsourcing methodology, which basically involved a track task for finding suitable annotators, training them, and often some arbitration or consolidation step to improve the quality of the annotation. And this controlled crowdsourcing provides kind of a midpoint between crowdsourcing in the wild, which may often not be good enough for such involved tasks, and expert annotation, which is usually not feasible. So we find it actually as a very effective methodology whose cost is pretty much like regular crowdsourcing, because after investing a limited amount in recruiting and training the annotators, then the actual cost of the actual annotation is the same as crowdsourcing in the wild. We follow the same common practices of generous yet reasonable payment for crowd workers. So the takeout from this part, this last part of my talk, as I'm approaching the end, is promoting the creation of data sets that capture natural representations of meaning, of knowledge, of semantics in texts. And the key idea here is that instead of basing the representation on some predefined schema of formal labels and relation types, etc., the representation itself involved natural language expressions. And this was exemplified by the QA-based approach, but it can be relevant for other examples. People tried similar approaches for annotating natural language discourse connectives to capture discourse relations. You could think of doing that for factuality, for modality, modeling scope of various textual phenomena, and so on and so forth. So it's up to the semantic community to try and figure out how some semantic phenomena that were previously captured through formal theories may be captured in a natural-based representation where the representation elements are natural language expressions. And of course, the huge benefit is that annotation can become scalable and reliable. If you think of the major annotation efforts like AMR, for example, these are huge efforts that are very hard to replicate and happen quite rarely. While when we work with this QA semantics approach, as we approach another thing, it's quite easy for us to just develop the annotation. It takes some effort to develop the annotation protocol for a specific semantic phenomenon, and then we just run the annotation, investing a few $1,000s at Mechanical Turk, and it's highly feasible. But then the advantage is not just crowdsourcing, but the aspect I want to promote here is that it's worthwhile benchmarking such semantic representations, natural semantic representations, because they may also be very appealing for downstream modeling. The nice thing about representing information through QAs is that these QAs are natural language elements. So now we can apply the full power of language models, right, our pre-trained language models, to represent these QA pairs and maybe infer that two QA pairs are paraphrastic, or maybe develop a model that detects entailment between QA pairs and make some inferences. So all the power we have already developed for raw text, we may now apply to our semi-structure kind of explicit representations of further, that do explicate some further semantic aspects of the text that might be harder to detect in the raw text completely implicitly. Yet these explicit, let's say, QA pairs are still enable us to perform various explicit representations where we seek control and explainability. We might choose, for instance, a summary, which question answer, the information of which question answer pairs to include in a summary, and then generate a text based on these question answer pairs. So we can get more control than if we use completely opaque representation in an end-to-end model. So from that perspective, I think this kind of semi-structured natural semantic representations provide a midway between formal representations, classical representations, and fully opaque representations of the end-to-end paradigm. And these are particularly maybe timely today as a way to provide generic kind of task-independent semantic infrastructure for downstream tasks. So concluding my talk as a whole, benchmarking guides research and how the field proceeds. And as I think some people feel, we might be approaching a crossroad and some glass ceilings. I was suggesting 3 directions in which we can improve our benchmarking to expand the scope of and the capabilities of NLP research and applications. The first was methodological. Try to simulate in your benchmarks downstream use of the models that will be developed by your benchmarks. Application scope, I was focusing on expanding NLP applications to the interactive setting. And with respect to NLP infrastructure, I was suggesting to expand and revisit semantic infrastructure and knowledge representation infrastructure through shifting from classical formal representation to semi-structured natural language-based representation that might be timely. Thank you for listening.